Welcome back to our higher level IB Chemistry video series. This is the first video in IB Chemistry topic 19, redox processes, where we will be looking at electrochemical potential and standard free energy change. Before watching this video, ensure you've watched our IB Chemistry topic 9 video series, as this builds on the content included there. In this previous series, we discussed the idea that the voltage running through the external wire of a voltaic cell can be measured using a modified voltmeter called a potentiometer. Doing so records a standard electrode potential value for a species, given by the symbol E. However, we stress that this must be done with reference to the standard hydrogen electrode. For the higher level syllabus, you're expected to describe it. Being half of a voltaic cell, it is a container containing an electrode made of platinum. It contains a solution of 1 mole per decimeter cubed H+. The electrode is positioned in a container provided with hydrogen gas at 100 kPa pressure and 298 Kelvin. This undergoes the following reaction, creating a standard to measure the electrode potential of another species against. The standard hydrogen electrode therefore has an electrode potential of 0 volts. By measuring the voltage of various species, a range of electrode potentials can be calculated, as found in section 24 of the data booklet. Note once again how each half equation is written in terms of reduction and has an associated electrochemical potential value. These values therefore indicate the tendency for reduction to occur, with more positive values indicating a stronger tendency to undergo reduction, i.e. strong oxidizing agents, and negative values indicating a weak tendency to undergo reduction, i.e. strong reducing agents. Knowing this relationship therefore opens the possibility for predicting which species would be oxidized and reduced from two half equations. For instance, let's say we were given the two following half equations. Fe2 plus 2e minus goes to Fe, with an electrode potential of minus 0.45 volts, and Cl2 plus 2e minus goes to 2Cl minus at 1.36 volts. Since the electrode potential for Cl2 is greater than that of Fe2 plus, chlorine has a stronger tendency to be reduced. Therefore, the Fe would be oxidized and its equation reversed. So, the Cl2 would gain its electrons from Fe, forming the overall redox equation of Cl2 plus Fe goes to 2Cl minus plus Fe2 plus. Summarizing this as a single rule, the equation with the less positive value of electrode potential will be reversed. Note, this flips the positivity of the electrode potential value, i.e., if the electrode potential for Fe to Fe2 plus 2e minus would be 0.45 volts. We can take this one step further and summate the values of each half equation to generate an overall cell potential value. When doing so, ensure you use the flipped value for the oxidized species. So here, 1.36 volts plus 0.45 volts equals 1.81 volts. If the cell potential is greater than 0, it indicates the reaction would take place spontaneously, whereas values less than 0 would not. It is important to note that the size of the value does not indicate the speed of the reaction, purely the likelihood. Let's look at an example to tie this all together. Predict if the following reaction would take place spontaneously within a voltaic cell. Mg solid plus lead 2 plus aqueous goes to Mg2 plus aqueous plus lead solid. So, to predict if the reaction will occur, we need to calculate the electrode potential for this reaction. We can see that we will be using the following half equations from the data booklet. However, since Mg is oxidized to form Mg2 plus in our equation, the first one would be flipped, along with its value, to give 2.37 volts. The overall cell potential would therefore be 2.37 plus negative 0.13, which equals 2.24. This is greater than 0, so the reaction would occur spontaneously. We can apply this concept of cell potential to cell notation too, as introduced in our standard level topic 9 video series. Since cell notation states the species oxidized on the left and reduced on the right, we can work out cell potential from cell notation using the formula cell potential equals electrode potential on the right hand side, subtract electrode potential on the left hand side. We can use values straight from a data booklet without flipping, since the subtraction effectively does this. Consider the same reaction in cell notation. Mg solid, vertical line, Mg2 plus, aqueous, 2 vertical lines, Pb2 plus aqueous, vertical line, Pb solid. Using the data booklet, we can see the electrode potential for Mg2+ is minus 2.37 volts, and Pb2+ is minus 0.13 volts. Therefore, negative 0.13 subtract negative 2.37 equals 2.24 volts. Easy. However, reactions are not always undertaken at standard conditions. You've now reached the end of the preview for this IB Science video. If you want to check out the full video, head over to our website and select a membership plan today.